Okay, so this lesson is about resonance and specifically the applications with strings and air columns. Let's start with just taking a look at what is resonance.
One of these things is not like the others. Which one is different? Do you know? Can you tell which thing is not like the others? I'll tell you if it is so.
Well, were you able to guess which video didn't belong? Did you use the title as a clue? If you guessed it was the father pushing his kid on a swing, well, you'd be wrong. While 3 of these videos seem much more destructive than the swing set, that's not what unifies them. Here, the odd phenomena out is the nuclear bomb. That's because the other 3 are all manifestations of a phenomena called resonance. The concept of resonance is one of the more spectacular effects in physics. It's the tendency of a system to vibrate or oscillate dramatically when it's driven at certain frequencies. We've all experienced this effect. It can be as enjoyable as being pushed on a swing, or as jarring as driving on the rumble strips on the side of a highway. Most of us have some intuition for how it works. Ask yourself, what's the best way to push someone on a swing? I suppose you could push them once, really, really hard, but this can have undesirable consequences. The best time to push them is when they've just started falling away from you. You can apply a small force over a fairly long time. It's now possible to build up a large height over many swings back and forth. If you remember trying to learn how to swing by yourself, you'll remember how important that timing is. If you don't pump your legs often enough, or pump them too often, you won't go anywhere. But if you pump them at just the right frequency, you can get going really high. I think most of you probably have some intuition for this. Who knew? You guys were all already experts in physics. Let's get a bit more complicated. The wine glass is very similar to the on the swing. Well, sort of. Hopefully the kid won't shatter. With the wine glass, sound plays the role of the pusher, while the glass plays the role of the swing. You see, sound is just a pressure wave traveling through a medium, in this case the air. When the waves hit the glass, it pushes the glass back and forth by a tiny amount. Just like the swing, if you push the glass too frequently or too slowly, it won't build up a large amplitude. In order for the amplitude to grow, the frequency of the sound has to match the natural frequency of the glass. If you're curious what that frequency is, ping the side of the glass. The sound you hear is the natural frequency. This happens to be around 500 Hz for many glasses, meaning you want the sound generated by the speakers to be around 500 Hz. If the volume of the speaker is high enough, and the sound waves hit the glass just right, the glass can be shattered by sound alone. The important thing to realize here is that it's not just the volume of the sound that breaks the glass. I guess you could try picking a random tone and cranking up the volume, but it would probably deafen everyone in the room. By hitting the resonance frequency, you can break the glass with a lower volume, because large vibrations can build up over time. And bonus, no broken eardrums. The last example of resonance we'll look at is a bit more abstract. It's the Tesla coil. A Tesla coil is basically a voltage transformer that lets you make impressive lightning shows. It's also my current project for the next couple of Idiots for Physics videos. Instead of physically vibrating, this system relies on a coil called an inductor and 2 conducting plates called a capacitor to move electrons through a circuit. The thing that's swinging back and forth is actually the electrical current. This is a bit technical and really deserves its own video, but just like the wine glass, driving the system at its natural frequency can produce some pretty spectacular effects. So there you have it, 3 examples of resonance. The reason I dedicated an entire video to this is because it's the perfect example of the power of physics. It's a single concept that unifies many drastically different phenomena. We can actually use this to make predictions about how other systems with natural frequencies behave. Studies have shown that students who come into university physics with the outlook that physics is a collection of unified concepts tend to do a lot better than those who view physics as a collection of disparate facts. So if you take one thing away from this video, take that concept. Physics is a unifying force for our understanding of the universe, not some collection of random trivia that has no bearing on real life. And if you need a more concrete example of the importance of resonance, well, this is what happens if you fail to take it into account. Thanks for watching. This episode was brought to you by the letters P, H, and D. You may not be able to heal anyone, but at least they have to call you doctor.
So an object is free to vibrate, will tend to do so at a specific rate, which would call its natural or resonant frequency. This frequency depends on the size, shape, and composition of the object, so each object will have its own resonance frequency, but such an object will vibrate strongly when it's subjected to vibrations or regular impulses at that same frequency. This phenomenon is called resonance, and through resonance, a comparatively weak vibration in one object can actually cause a very strong vibration in another. Now, in the last video, we talked about what could happen if you didn't take resonance into account. We're going to just watch another video specifically about that Tacoma Narrows Bridge. Now that Tacoma Narrows Bridge was actually built in 1940. It opened on July 1st and it lasted only a couple of months. November 7th was the date that it collapsed the same year. And really it was just because the wind vibrated this at just the right frequency, pushing it a little bit more each time, similar to a child on a swing or the glass. The universal wave equation, V is equal to the wavelength times frequency. We need to remember that, but the resonance frequency is going to happen specific for strings and air columns based on the wavelength that will help us to determine velocity and frequencies. Now, all items have this frequency. It's determined by the speed of the wave through the material and the length of the object, and the trick really is to find that proper wavelength whenever we're talking about strings or air columns. So, with strings, depending on the length of the string, what we can see is that this length will vibrate at exactly half a wavelength, or 1 wavelength, or 1.5 wavelengths. They're always going to be multiples of half a wavelength, and we call that the first, second, and third harmonic. Okay, let's take a look at what that might look like.
तो अगर मैं इसको इस तरीके से मूव कर रहा हूं तो यहाँ क्या हो रहा है, इधर नोट, उधर भी नोट, और बीच में क्या है, एंटी नोट। और ये जो बीच का रीजन है, दो कंसेक्यूटिव नोट्स के बीच का जो रीजन है वो कहलाता है एक लूप। ये बात समझ में आ गई क्या? ये कहलाता है आपका सेकंड हार्मोनिक, या फंडामेंटल मोड के बाद जो अगला मोड होता है वो यही होता है। यहाँ पे आप देखेंगे एक नोट ये रहा, एक नोट वो रहा, एक नोट वो रहा, और बीच में क्या है, बीच में यहाँ पे दो लूप बन रहे हैं, दिख रहे हैं क्या? यहाँ पे दो लूप बन रहे हैं। एक नोट बिल्कुल यहाँ मेरे मुंह के सामने, ऊपर लिखा हुआ भी है, ये लिखा ऊपर, ठीक है। एक नोट इधर है, एक नोट इधर है, और बीच में यहाँ पे दो लूप बन गए, 2 एंटी नोट भी आ गए। तो 3 लूप अगर बनाने तो वो इस तरीके के बन जाएंगे।
And this third harmonic is 1.5
एक नोट वो रहा, एक नोट ये रहा, एक नोट ये रहा, 4 नोट हैं।
So let's take a look at an example. If we've got a 90 centimeter or 0.9 meter string vibrating at its fundamental frequency, that's half a wavelength of 80 hertz. What is the speed of the wavelength traveling through the string? Well, first of all, that half a wavelength is 0.9 meters. And therefore, a full wavelength is going to be, well, double that. So times thing by 2, that means the wavelength here, as it's vibrating at its fundamental frequency, is actually 1.8 meters. Now, we do have the frequency also of 80 hertz, which means we can use that universal wave equation and plug in the numbers for wavelength and frequency to find the speed of the wave. And you're going to find that speed of the wave is traveling at 144 meters per second through that string. Okay, I would like you to try this one. Pause the video and see how you do. Okay, welcome back. We take a look. We've been given the second harmonic, which is 1 full wavelength. So that wavelength is actually going to be 0.6 meters. The frequency being 350 hertz means that the wave is going to be traveling through the string at 210 meters per second, or 210 meters per second. Now with air columns, this is a little bit different. It depends on whether they are closed or opened. This side showing the closed columns, this side being the open columns. Notice the closed column, it's 1/4 of a wavelength, or 3/4 of a wavelength, or 1 1/4 wavelengths, right? We've got a full wavelength plus 1/4, because here with the closed column we need that amplitude, the maximum, happening at a position where we've got the opening. With an open column, we need that happening on both ends in order for us to get that maximum amount of sound. Right? So what we're going to do here, so half a wavelength, 1 wavelength, 1.5 wavelengths, similar to strings. So in this little video, what we're going to see here is a closed air column, because it's bottomed out by the water, and the water's going to drain out, and we're going to have a speaker on the top. And what we'll see is that there's periods where it's loud, periods where it's louder, where we've reached those frequencies. First, third, fifth harmonic. And there's spaces where it's quiet is going to be where this is not happening, where we got lengths that are different than this based on the sound of the air and the length of the column, because we're constantly adjusting the length of that column. There you can see the speaker on top. So I hope you heard that the sound went louder and quieter based on the length of the tube, seeing if you wound up with a resonance frequency or not. Let's take a look at example number 2. A closed air column resonates with a fundamental frequency of a quarter wavelength of 225 hertz. What's the length of the air column if the speed of sound in air happens to be 341 meters per second? So we know that this column, right, is going to have a length, but this length here is what we're looking for. We know it's 1/4 of a wavelength, right? And so we need to first of all find the wavelength. Well, given the universal wave equation, the velocity is equal to wavelength times frequency. Right, we'll take the velocity and divide by the frequency. So that 341 divided by 225 gets us the wavelength of 1.51 meters. Okay, so the wavelength, this is this closed air column has a wavelength of 1.51 meters, which is 1/4 of a wave, but the length of the column is only 1/4 of that wavelength, or 1/4 times 1.51. Which gets us 37.8 centimeters. Right? All of these strings and air column questions are really just applications of that universal wave equation and the concept of resonance. Try this one. Give the video a pause and then see how you do, and check in a moment. Okay, welcome back. You should have noticed that here that if the air column is 0.5 meters and that represents half a wavelength, then the wavelength is actually just 1 meter. And so the velocity, the speed of sound in this case, is 337 meters per second. Now you may have noticed that the speed of sound in this try this is actually different than what you had in the example. Speed of sound is not a constant the same way that the speed of light is. So just note, for all quizzes and tests, I will provide either a diagram as drawn or a wavelength with clue as written to aid you in answering your questions. Remember that speed of sound is not constant, but depending on humidity, pressure, density, but generally the speed of sound in air will be around that 340 meters per second mark. Okay, if you do have any questions, please let me know, and thanks for watching.